The space industry is an exciting and demanding field for materials research. As the drive to push beyond our home planet increases, the demand for materials that can thrive in the highly stressful environments in space continue to increase. In space, materials face some of the harshest conditions engineers must design for. As we move on into a new era of manned spaceflight led by NASA's Space Launch System and SpaceX's Starship Super Heavy Launch Vehicle, there's an increased need for human-suitable conditions. In human spaceflight, one design factor that is often overlooked are windows. In an unmanned flight, windows are completely unnecessary as there is nobody inside. Visual feeds are streamed to launch control and flight control teams by a series of cameras placed on the outside of the craft. In manned spaceflight, windows are necessary for astronauts to perform their job optimally, as well as to provide some comfort in cramped conditions. The problem with this is that windows are not particularly good for building structures. Materials engineers must design around this to produce the best possible product for their given requirements. Given the renewed interest in lunar missions due to the Artemis program, I will focus on windows used in travel to the moon and back. There are significant design challenges for any materials going to space, especially the windows. Spacecraft experience extreme temperature variations due to space environments. On the moon, temperatures can range from 260 degrees Fahrenheit to negative 280 degrees Fahrenheit, and during re-entry, the temperatures on the surface of a vehicle can reach as high as 5,000 degrees Fahrenheit. It doesn't take a rocket scientist to recognize humans wouldn't survive these conditions, and so not only do any materials need to survive these conditions, they also need to protect astronauts from extreme temperatures. There is also a variety of physical stressors that require the windows to be strong, hard, and tough. During launch, spacecraft experience violent vibrations and materials must be resistant to vibration fatigue, otherwise the risk of deformation and fracture is significantly increased. Along with thermal protection, a window needs to be strong enough to withstand the pressure difference between the vacuum of space and the crew compartment. Another factor to consider are impacts with a launch vehicle. While the risk of something like bird strike or space debris is pretty low, and much effort is undertaken to prevent such risks, the risk factor needs to be kept as low as possible by layers of redundancy because any small oversight could result in a catastrophic disaster. It's also worth noting that weight should be minimized because getting things into space is expensive. And of course, a window needs to function properly as a window. The material selected needs to maintain transparency with as little optical distortion as possible. To solve all these issues, a multi-material approach is used. During the days of the Apollo program, the windows were made of multiple glass panes from different processing methods to favor certain properties. There were 3 glass panes used. The outermost pane was made of highly pure fused silica. This acted as a thermal insulator. Fused silica is desirable for its very low coefficient of thermal expansion and its very low thermal conductivity. The middle pane, often referred to as the redundant pane, was made from the same material as the innermost pane, aluminosilicate. Aluminosilicate is a common glass composite well regarded for its combination of hardness and transparency. It's still heavily used today in cell phone screens. The panes were supported by a seal of silicone elastomer. This protected the windows from vibrations and provided an airtight seal. Since the Apollo days, advancements have been made in the materials department. The latest manned space capsule, Orion, bears many similarities to the Apollo space capsule, though there have been many improvements. In the windows, glass is beginning to be phased out. There are several issues with glass that don't make it optimal for space applications. While glass is quite hard, it's very susceptible to degradation and fatigue when a load is placed on it. Glass also has a very high propagation of defects, meaning if anything goes wrong with the material, an accident can quickly become catastrophic. There are a few features of the Apollo window design that are still used on Orion though. The Orion spacecraft window still features a 3-pane design. The outermost pane is still made of fused silica for thermal protection, and the windows are sealed in using silicone elastomer. The primary difference, though, is that the 2 innermost panes that provide pressure containment are made of acrylic. The switch to acrylic has several main advantages that I will cover, along with further detail on the fused silica. Often with materials, you can't find a perfect material that suits your every need, and that's why multiple materials are often used. Different materials suit different roles, and that's exactly what is done with the Orion windows. As I mentioned earlier, fused silica is often in space applications because of its relatively high strength, low thermal conductivity, and low coefficient of thermal expansion. Glass has been used and manufactured for thousands of years, but for applications such as these, precision is paramount in order to minimize defects and optimize the properties. Glass is notably an amorphous solid. Glass is normally formed by taking small crystals such as the quartz and sand and superheating it such that it forms a highly viscous liquid. This liquid is then cooled very quickly such that the sample doesn't have time to form a crystal structure. This causes the glass to maintain the amorphous structure of a liquid while in solid form. While this method works for many applications, sometimes high precision is needed. In this case, a method like chemical vapor deposition is performed. In chemical vapor deposition, chemical vapors that contain the silicon and glass are deposited onto a surface, where the silicon nanoparticles fuse to a surface under high heat. The other chemicals in the vapor are pumped out as the silicon fuses. The nature of chemical vapor deposition means that the fused silica is deposited very precisely, and engineers can highly optimize the properties. Since the glass has very few defects, the crack propagation is reduced, strength is increased, toughness is increased, and the optical properties are much more reliable. The glass is extremely clear, and it reflects so little that the Apollo astronauts were able to make orbital calculations based on markings placed on the window. The improved strength combined with its excellent thermal insulation and low expansion means that fused silica is very well suited for its job as a thermal protection layer. As also mentioned earlier, the aluminosilicate glass used in the inner layers has been replaced with acrylic. The use of acrylic has been very beneficial to the Orion spacecraft. Acrylic is lighter, stronger, and easier to machine than glass. Acrylic is about half as dense as glass, meaning they have been able to reduce the weight of Orion by more than 200 pounds. That's hundreds of thousands of dollars saved in fuel costs. Acrylic is also much tougher than glass, around 10 to 20 times stronger. Its toughness makes it a much simpler to machine, and this also heavily reduces production costs. Acrylic is very high clarity. In fact, it has a higher light transmittance than glass. Acrylic is the common name of methyl methacrylate. Methyl methacrylate is formed by reacting acetone with sodium cyanide to produce acetone cyanohydrin. This is then reacted with methyl alcohol to finally produce methyl methacrylate. This chemical is then cured over a several-day period and is machine polished to meet NASA's precise standards. Acrylic's low weight, high strength, and incredible optical properties make it a material perfectly suited to maintain the pressure of the vehicle. Once NASA receives these materials, they undergo rigorous testing to make sure there are no mishaps that could interrupt important missions and cost the agency billions. Every window has undergone heavy vibration and vacuum testing and has been measured down to the tens of nanometers to make sure that everything is exactly as it needs to be.